All right, thanks. Go ahead,
Okay,
Kazhdan.
hopefully everybody here and on Zoom can hear me. So the work I'm going to be telling you about is joint with Ibo Gao. So pattern heights and the minimal power of Q in a Kazhdan-Lusztig polynomial. I'm going to first tell you what Kazhdan-Lusztig polynomials are. So this is just an overview slide of where they're coming from. I'll give you a definition in a second. The Kazhdan-Lusztig polynomials, denoted PUV, they're polynomials in a single variable Q. They're indexed by a pair U and V of elements in a Coxeter group W. If you prefer, you can think of the Coxeter group as being the symmetric group. So they're polynomials indexed by a pair of permutations. The introduction of these, which was in the late 70s, was one of the sort of founding papers of geometric representation theory, because it turns out that these polynomials are related to several not obviously related structures in algebra and geometry. So on the one hand, they tell you about the singularity of Schubert varieties. These are varieties in the flag variety that were implicit in the last talk. They also tell you information about representations of the corresponding Lie algebra. So if W is the symmetric group, this Lie algebra will be the Lie algebra for SLN, for example. And they also tell you about the Heck algebra of W and its representations, or we could specialize and get information about representations of the symmetric group or the Coxeter group itself. So I've written here that these are polynomials with natural number coefficients. Excuse me. The definition will it will only be clear a priori that they have integer coefficients, and the positivity of the coefficients is a very deep fact. Okay, so they are related to these various algebraic and geometric objects, but they're polynomials indexed by, say, a pair of permutations, and so we hope to understand them to the extent possible in terms of combinatorics of permutations and so on. The combinatorics that shows up is, in part, the combinatorics of Bruhat order. So we already saw this in the last talk. This is the strong order that Tianyi mentioned. So on the left, this is what the order looks like for the symmetric group S3. You notice in particular that the poset is graded. So it's graded by the length of the permutations, which is the same as the number of inversions of the permutation. And the cover relations correspond to swapping two elements of the permutation in such a way that the length increases by only one. You'll see already for S4 on the right that this poset gets quite complicated quite quickly. All right, here is the first of two slides giving you the definition of these polynomials. I certainly don't expect you to absorb everything here. I'll point out a few features that you should pay attention to. So the first is that these polynomials are zero unless U is less than V in Bruhat order, in which case they are non-zero. So that's the first place Bruhat order comes in, so we should really be thinking only about pairs U less than V. The polynomials are 1 if U is equal to V. There's this degree bound here. So the degree is on the order of the difference in length between V and U. And then there's this recursive formula expressing, well, the sort of reversed version of one Kazhdan-Lusztig polynomial as a sum over the elements of this Bruhat interval times some smaller Kazhdan-Lusztig polynomials with these coefficients which are R polynomials. Okay, I have to tell you what these R polynomials are now. So these are likewise polynomials with integer coefficients. Now these will have genuinely positive and negative coefficients. Again, they're zero unless U is less than V. If U and V both have a common descent, so in the symmetric group, this is about them both decreasing, say, from position I to position I plus 1, then I can multiply both U and V by the corresponding simple reflection and have an equality of the R polynomials. The most interesting case is this one here, where we have a descent of V, which is not a descent of U, and then we get this linear combination here. And we can apply this recursion until we get down to one of the base cases, in which case we can evaluate our polynomial. I'll point out this Q minus 1 here. This introduces signs. So there are signs in the R polynomials, and therefore signs in this formula here. And it's not at all clear that these P polynomials have non-negative coefficients, but in fact they do. Okay, I will now tell you about the particular aspect of these polynomials we're going to be interested in, which is sort of the first non-trivial power of Q appearing. So to set the stage, I want to talk about this theorem. So this is really a concatenation of several theorems due to Kazhdan, Lusztig, Peterson, and Lakshmi-Bai-Sandhya. So if W is simply laced, so in particular for the symmetric group, the following are equivalent. So one is that the polynomial PEW, so here E is the identity element, is just the constant 1. That's equivalent to the XW here. This is the Schubert variety being a smooth variety. That's also equivalent to the Bruhat interval between the identity and W being rank symmetric, that is having the same number of elements on the ith level from the bottom as on the ith level from the top. And lastly, to W avoiding these permutation patterns, if indeed we're in the symmetric group. So what it means to say contain a pattern 3, 4, 1, 2 is if I write the one-line notation of my permutation, then I look for subsequences of the indices such that those values are in the same relative order as 3, 4, 1, 2. Okay, so this was one of the first places that permutation patterns appeared, and this is a very nice theorem of, this last point is the Lakshmi-Bai-Sandhya theorem. For example, if we looked at P from the identity to 3, 4, 1, 2, well, 3, 4, 1, 2 itself certainly contains the pattern 3, 4, 1, 2, and therefore doesn't avoid it. So the polynomial should be not just 1, and indeed the polynomial is 1 plus Q. We see on the right here, this is what the Bruhat interval below W looks like, and we notice that there are 4 elements in the first rank below the top, and only 3 here. So that is not rank symmetric. Okay, as I alluded to several times, if V is less than W, then these polynomials indeed have natural number coefficients. So they have non-negative coefficients. And it's a major open problem to give any sort of positive combinatorial formula for these coefficients. They are natural numbers. We would like to understand what natural numbers they are. So one case is easy. So it turns out that the constant term of all of these polynomials is always 1. So these polynomials are always 1 plus some positive multiples of Q. What we're going to focus on in this talk is studying the next term in such a polynomial. So let's assume that we have an element such that the Schubert variety is singular, that is not smooth. The smooth ones we saw on the last slide, the polynomial is just 1, and the smooth ones are a vanishing fraction of all the Schubert varieties. So that case is understood. But let's assume we're not smooth, so in particular the polynomial is not just 1. So there is some next term if I write my terms starting with the lowest power of Q. So I will write h of W for this power, that is the smallest positive power which actually appears in the polynomial. So my polynomial looks like 1 plus some multiple of some non-zero multiple of this coefficient plus some higher order things in Q. Now, there's this theorem of Bjorner and Ekkedal, which on the one hand tells us a way to get our hands a little bit on this coefficient h of W, and also tells us one reason we might care, which is that for a singular Schubert variety, this h of W defined on the last slide is the first rank for which my Bruhat interval is not rank symmetric. It's the smallest I, such that the ith rank is not the same size, and in fact will always be smaller than the ith rank from the top. So I'm writing sub I here means the ith rank of this Bruhat interval, the elements of length I. This then is the first cohomological degree in which the Schubert, this cohomology group is smaller than the the cohomology group coming from the top. So this is sort of the first homological degree in which Poincare duality fails, in some sense, for the Schubert variety, which is, because it's singular, this Poincare duality can fail. Now, there's this conjecture which will be what we're most interested in. So this is due to Billy and Postnikov. They conjectured that for W finite of simply laced type, so type A, D, or E, type A being the symmetric group, and having rank R, if we have a singular Schubert variety, then this H of W should be at most R. Now, this is somewhat surprising because if you recall from the definition of the Kazhdan-Lusztig polynomials, the degree of these polynomials was bounded by the length difference between the two elements. In particular, the degrees can approach the degree of the longest element in the symmetric group, which is n choose 2, or rather the length is n choose 2. So the degree of these polynomials can be on the order of r squared. But what we're saying here is that if the first r coefficients were to vanish, then in fact the whole polynomial must be trivial. So that's a bit unexpected.
So do you actually know that you could achieve that order? Or is that's just a bound?
That's a bound, but I believe you can get close to that. Certainly you can get superlinear, but I'm not sure whether you can actually get quadratic. It's a good question. Okay, so the combinatorics that's going to be involved here is now again related to patterns and some of the same patterns we saw before, but now taking into account more refined information about how the pattern is occurring. So suppose I have these indices, which are the positions of a 3, 4, 1, 2 pattern inside my permutation W. We're going to call the height of this occurrence, it's W of I1 minus W of I4. So we look at the number playing the role of the 3, and we subtract from it the number playing the role of 2. So this will always be some positive number. The minimum height of the permutation is the smallest height among all occurrences of 3, 4, 1, 2 in W. So for example, 3, 4, 1, 2 itself, well, has one occurrence of 3, 4, 1, 2. 3 minus 2 is 1, so it has min height 1. If my permutation were instead 4, 5, 3, 1, 2, this has an occurrence of 3, 4, 1, 2 as the 4, 5, and 1, 2. So here 4 is playing the role of 3, so I take 4 minus this 2, and that's 2. So this notion of min height has occurred before. So for example, in this work here of Cortez, was studying classification of the singular locus of Schubert varieties in type A, and Wu was studying Kazhdan-Lusztig polynomials which are just equal to 1 plus q to some power, and that's it. So this notion has appeared before. So here's our first main theorem. We show that if we're in type A, and if W is singular, then here is an exact formula for this first non-trivial power appearing, h of W. So this is 1, that is, there is a non-zero coefficient of q in the polynomial if W contains the pattern 4, 2, 3, 1. If it doesn't contain 4, 2, 3, 1, then since it's singular, it must contain 3, 4, 1, 2. And in that case, h of W is given by the min height, which involves the pattern 3, 4, 1, 2 as we just saw. So for example, if this is our permutation, which we saw had min height 2, we can inspect this for a little bit and see that it avoids 4, 2, 3, 1. So we know the min height is 2. So it's supposed to look like 1 plus some multiple of q squared plus, well, because of the, it could have more terms, but it turns out just to be that that's the entire polynomial. And h of W is 2, agreeing with the min height. Okay, it will turn out, if we think about this a little harder, that this implies the Billy-Postnikov conjecture in type A, but we'll see that example in a little bit. So lastly, I want to expand to finite simply laced types, so including D and E, and to try to prove the remainder of this conjecture of Billy and Postnikov, which was the upper bound of R being the rank of the simply laced group. So here's the theorem. We prove Billion-Postnikov's conjecture, and in fact, the R that they had can be replaced with R minus 2, and this bound is tight in all of these types. So let's see in type A how that follows from the theorem, the exact formula for H of W that I showed you previously. That's right. Rank of the Coxeter group is the number of nodes in the Dinga diagram. So symmetric group Sn, for example, has rank n minus 1. Let's think about how we could maximize min height of W and therefore maximize H of W in the symmetric group. Well, if I've got a 3, 4, 1, 2 pattern, the role of the 3 cannot be played by anything larger than n minus 1 because there must be some larger number playing the role of the 4. And similarly, the 2 cannot be have its part played by anything smaller than 2. So we can maximize the min height by taking this permutation, n minus 1 n, and then having all the intermediate numbers decreasing here in sequence, and then at the end having 1, 2. So this has min height n minus 1 minus 2, which is exactly the rank of the symmetric group minus 2, achieving this R minus 2 here. For types D and E, we prove the upper bound, and indeed it is tight, but we don't have an exact formula that applies to all elements. Let me briefly comment on what goes into proving these theorems. So I showed you this Lakshmi-Bayi-Sandhya theorem before characterizing smooth Schubert varieties in terms of pattern avoidance. There are several characterizations of smooth Schubert varieties in other finite types other than the symmetric group. One in terms of signed patterns due to Billy, and one which sort of groups the signed patterns together in a more uniform root theoretic way due to Billy and Postnikov. Interestingly, in this work, it's important that we take sort of a hybrid between those two characterizations. So the sign patterns, there are many, many patterns, and in the root system patterns, there are very few. But here we need to sort of take an intermediate grouping and address those groupings individually. So for example, we're interested in some type A3 patterns inside type D, and it turns out to matter whether the subsystem you're thinking about is conjugate to sort of the A3 that lives on the double leaf side of type D, or whether it corresponds to some A3 living inside the sort of backbone. Then what we do is we take these appropriately grouped families of patterns, and we show that for certain of them, if you contain this pattern, then we understand the Bruchau interval explicitly enough to know that H of W is 1 or 2 using the Bjorner-Eckert result about the first place that the ranks sizes differ. I should mention that it's almost impossible to prove any of, well, I have no idea how one would prove any of this directly from the definition of the Kazhdan-Lusztig polynomials. Because there's all sorts of cancellation, it's extremely hard to control whether certain coefficients are in fact vanishing or not. Lastly, if you avoid these certain special patterns that appeared in the second step here, then we understand the structure of these elements very well, and we can find particular parabolics such that if I project from the full flag variety to a partial flag variety, and look at that projection from a Schubert variety to a Schubert variety in the partial flag variety, then in fact all the fibers of that projection are isomorphic, and so this is this upstairs Schubert variety is a fiber bundle over the downstairs one. And in this case, we can understand this interval in terms of an interval in the parabolic quotient and a smaller Bruchau interval. And so we can inductively understand what these intervals look like and apply Bjorner-Eckert criterion. That's all I have for you. Thanks.
All right, are there any questions for Christian? All right, we'll go with Sarah first, and then there are a couple down here.
Nice talk. I've been wondering if you can also say something about the minimal coefficient with a non-vanishing coefficient for Kazhdan, more general Kazhdan Lusztig polynomials with u and v, right? Because they might be larger than h of w.
Right. Yeah, we looked at that, and there's probably some way that one could combine what we do, at least in type A, with so in type A only, there is a known classification of the singular locus of the Schubert variety, and there seemed to be some way that you could keep track of how many elements of the maximal singular locus you're less than, and exactly your relationship to the set of components of the singular locus, and combine that with this formula in some way, but we didn't work out the details of that.
Questions? Do someone down here have a question?
There's one over there.
Oh, over there. All right, was there one up there first while I go this way? Okay, yep, Sam.
Yeah, really nice talk, Christian. So this is a question maybe about intuition, which, as Rosa told us earlier, is a slippery concept, I guess. But so you kind of said a couple times that you thought this was like a surprising, the conjecture and the result is sort of surprising, the fact that min degree is less than the rank, because it could be like quadratic or something, the degree of the polynomial altogether. But I'm wondering why you think that's surprising, considering that if Kazhdan Lusztig polynomials were just completely random polynomials, right? Wouldn't you expect them to have a linear term, and so the min degree would be 1? Or
well, okay. So one thing that surprised me is I knew already of this result of Polo that in fact any polynomial with constant term 1 and non-negative coefficients does appear as some Kazhdan Lusztig polynomial in the symmetric group. So I kind of thought that would preclude nice things like this happening, but in fact it doesn't, because, well, this result would say that for certain of those polynomials, in order to realize them, you're going to have to look in very high rank. So that wasn't the fact that these polynomials can be sort of arbitrarily bad was in the back of my mind as being an obstacle to proving something like this.
All right, question over here.
Hi, can I ask a silly question? So about your h of w bound, do you have any idea how the values are distributed, or like whether you expect like a typical example to be far away or close to it?
I couldn't quite make out what the question was.
Oh, okay, so you had this bound for h of w. My question was, do you expect a quote-unquote typical element to be far away, or like do you have any idea how the values are distributed in some sense? Or is this a reasonable thing?
Right, so I think the question is, what would the distribution of this h of w look like? So I would suspect that most elements have small h of w. So certainly a generic element does contain 3, 4, 1, 2. And I would suspect that it's going to contain relatively small height 3, 4, 1, 2s, but I don't have any numbers to offer you. Yeah. Certainly it's the case if you look in low rank groups, well, a lot of the polynomials are just 1 or 1 plus q. Certainly the intuition from low rank groups is that most of the polynomials will have small h of w.
Okay, I think there's a question up here.
Sorry? Right. Okay, yeah, that's right. Yeah, okay, Joel's got a great point. A generic permutation will contain 4, 2, 3, 1, and therefore will fall into the first case of the theorem with having h of w equals 1. So that's right. So we do know that almost all permutations will have h of w equals 1. If you look inside the 4, 2, 3, 1 avoiders, then one could ask about that distribution. That would be interesting. Yeah.
Okay, go ahead.
So, so you have this pattern formula for type A. How do you prove this bound conjecture for types D and E?
So type D was via the strategy that why is it at most R? The strategy I outlined is using this fiber bundle structure and iteratively getting down to things that you understand explicitly enough that we can see that the bound holds and bootstrapping back up. Type E, so type E, the calculation was originally done in the Billy Postnikov paper where they make the conjecture. They had conjectured it for type E, but even there, in order for the computation to be tractable at all, they also had to use, they didn't quite state it in these terms, but similar decomposition of the intervals in order to make that computation tractable.
Any other questions? Okay. Oh, Joel. All right.
What can you say about the value of this non-zero coefficient?
Okay, great question. So the question is, what about the value? That is, we know that q to the h appears. What's its coefficient? Yeah, so there's work in progress with, which was part of the Mirawak program at Minnesota. So I've got a group of 6 or 7 Minnesota grad students thinking about that. And roughly speaking, it seems like you can count how many times the appropriate patterns occur, and the more times it occurs, the larger that coefficient's going to be. But there are caveats to that, and you have to be careful which ones are really giving you independent contributions to that coefficient. But I am somewhat optimistic that one could actually get a combinatorial interpretation of that coefficient as counting occurrences of the right kinds of patterns.
All right, let's thank Christian again.